Welcome back. This is an additional application of the graphical approach that I introduced in the first two screencasts that are on this YouTube channel. And here I'm just applying it to another crystal and showing how we get there for additional exercise for those who are interested in this. So imagine that you have a material and you know that material is a solid with a point group D3d. Now the question is, so this is what you know the point group, and you want to know what are the Raman active modes and then what are the polarization effects. So the first steps is always the same. The first is to find the character table of the group, so D3d, and find the Raman active mode. And you know the Raman active mode actually those modes that behave like rotations or like quadratic functions. So that would be this one and this one, and you see this by looking at this column here with either rotation, or sometimes you have x squared, y squared, z squared, that kind of thing, x, y, and so on. So these are the two modes that are Raman active. Actually, there are three modes since EG is doubly degenerate. Now, what you need to do to get the polarization effect and to see how the Raman intensity actually works, you need to find the tensors. And for that, you can also find table. I find it particularly useful to use the Bilbao crystallographic database, which is a freely available tool, which is really cool and has lots of features. Strongly recommend it. And when you look for the Raman tensor, you find those three tensors right here. So you see they look a little different from the one that we look at for the MOS2 that we did in the first two part of this series. Well, A1G looks very much the same as the one we had before, but the EG1 and EG2 are different. So let's try to see the polarization effect. And again, we are going to use this setup where we have the halfway plate and the incoming and outgoing light go through the halfway plate. So that's what we are going to look at. Okay, so we are going to do this geometrically and graphically, and we will suppose we'll start from 1, 0, 0. The A mode is given there in AAC. And then we can look at, we start from 1, 0, 0. So as the light goes through the halfway plate, it gets rotated. As you remember, the halfway plate also introduces a phase shift for the Y component, if it's the fast axis, but we don't have a Y component here, so the rotation is right here. Then, of course, this is now the light is actually goes through the Raman machine, so it's scattered by the Raman machine. And we see this as the effect on the polarization, the effect of the tensor on the polarization. So in that case, what we end up with is, of course, since we have A and A on the first two diagonal term, we have a collinear, scattered in a collinear polarization. So the polarization will be like this. Of course, it's the length of the blue arrow is going to be A. Now, this light goes through the halfway plate again. So there is first a pi shift, and then a rotation by theta. And so we end up with the green arrow. And now, if we measure the polarization at the level of the analyzer along the 1, 0, 0 direction, we find the length of the green arrow, right? It's going to be A. And if we look at 0, 1, 0, we find 0 because, the green arrow is always perpendicular to the 0, 1, 0 axis. Now it's a bit more interesting to look at the E mode. So we're going to look at both modes separately. So we're going to start with the E1 mode. And we start from, again, 1, 0, 0. We have a rotation of theta through the halfway plate. Now, this particular polarization, this particular tensor is going to essentially change the sign of the Y component and then reduce the length, right? So we are changing the sign of the Y component and reduce the length. And this lives, so the blue vector lives on this circle of radius C. Now again, this the light goes through the halfway plate, so we get this one for the pi phase shift, and then we have a rotation by theta. And then, of course, now we can calculate the Raman intensity, which is the square of the projection of the green arrow on either the x-axis or the y-axis. So on the x-axis, we see that we have c square, so the length of the green arrow, times the square of cosine 2 theta, because 2 theta is the angle with the horizontal. And likewise, if we measure along the 0, 1, 0, we find c square sine square 2 theta. So in the previous screencast, there was a small mistake about the color of the arrows, which I noted in the comment. This one there is no mistake. Now we can also apply this to the E2 mode, which is different than what we've seen so far. We start from 1, 0, 0, we rotate, same business. And after that, we have to apply the Raman tensor. And so the Raman tensor, the idea is that if you look at it very quickly, you see that if we consider that only a vector in the xy plane, that the G, the polarization, is going to, we are going to swap the horizontal and vertical component. We are going to scale it down by a factor c, and we are going to move it to the negative side. So this is something you do, you can think about it, but really, if you have an angle theta here, you're going to end up with the blue arrow. So if you have trouble with this, just pause the screencast and think about it, and you will see that it's actually pretty straightforward. Of course, this angle here is theta. Now, this blue arrow lives on the circle of radius c. Now we can go through the halfway plate again. So we have this, of course, and then we have, of course, at an angle theta, and then we have the rotation by an angle theta again. Okay. Now we are in a position to calculate the Raman intensity, which will be the projection of the green arrow either on the x-axis or on the y-axis. So if we have a projection on the y-axis, that's going to be the vertical dimension here. And of course, the dimension is going to depend on c squared cosine square 2 theta. If you have trouble picking sine and cosine, you think about if theta is equal to 0, the green arrow would be vertical, therefore it has to be a cosine. Okay. On the other hand, the other direction is going to give you c square sine square 2 theta. So you see this graphical approach is really powerful. Again, I apply this to a particular setup, but you can apply this to any different setup, and that allows you to really follow the polarization and look at the process really through the optical path. So I hope this was useful as an additional application of what I explained in the first two screencasts. Thank you very much.